Hello students, in previous class we discussed activity. So what is that activity? When light travel from rarer to denser medium, then what happen? When light travel from rarer to denser medium, then the refracted ray move towards the normal and the angle of refraction is less than angle of incidence. Today we are discussing one more activity. What is that activity? What happens when light ray travels from a denser medium to rarer medium? To perform this activity, we need one metal disc, protractor, and transparent vessel, water, straw. First, take a metal disc and use a protractor and mark the angles along its edge as shown in the figure. First, take a metal disc and use a protractor and mark the angles along its edge as shown in the figure 5th A. Arrange two straws at the center of the disc in such a way that they can be rotated freely about the center of the disc. So in figure 5b, we immerse straw. In that red colored lines we can observe two red colored lines. So that are nothing but two straws. Okay, we arrange two straws at the center of the disc in such a way that they can be rotated freely about the center of the disc. Adjust one of the straw to make an angle 10 degrees. Immerse half of the disc vertically into the water filled in a transparent vessel. While dipping, verify that the straw at 10 degrees is inside the water. So we adjusted one of the straw to make an angle 10 degrees and we immersed half of the disc vertically into the water filled in a transparent vessel. While dipping, verify that the straw at 10 degrees is inside the water. From the top of the vessel, try to view the straw which is inside the water as shown in the figure 5th B. Then adjust the other straw which is outside the water until both the straws appears to be in a single straight line. Here we adjusted two straws. One straw is making angle 10 degrees. So that immerse half of the disc vertically into the water filled in a transparent vessel. While dipping, verify that the straw is at 10 degrees inside the water. So we are immersed metal disc into the water, no? So when we are immersing metal disc into the water, that the straw which is at 10 degrees, that should be inside the water. Next, from the top of the vessel, try to view the straw which is inside the water as shown in the figure 5th B. Then adjust the other straw which is outside the water until both the straws appears to be in a single straight line. So one straw is inside the water. Okay, from the top of the view, from the top of the vessel, we are trying to see the inside straw. Okay, next, then adjust the other straw which is outside the water until the both straws appears to be in a single straight line. Means here one straw is inside the water, one straw is outside the water. So by seeing the inside straw, the straw which is at outside, that should be adjusted. When we are adjusting the straw which is at outside, we should see that the inside straw and outside straw will be in the same straight line. Then take the disc out of the water and observe the two straws on it. Take out the disc. Okay, then take the disc outside of the water and observe the two straws on each. So you will find that they are not in a single straight line. So next, take the disc which is outside. Take the disc outside of the water. Okay, we should take out the metal disc outside and observe the two straws on each. So then we can observe that they are not in a single straight line. Okay, the two straws are not in straight line. Why do the stars appears to be in a straight line when we view them from the top? So when we are seeing from the top, why the two stars appears to be in a single straight line? Next, measure the angle between the normal and second star and draw the table 2 again in your notebook and note the values. Do the same for various angles, means here we perform this experiment from 10 degrees, no, next perform the same experiment from 20 degrees, 30 degrees, by keeping the star at 20 degrees, 30 degrees, 40 degrees, 50 degrees, like that. Okay, and then observe the outside star. Okay, arrange the outside star that should be in the same line with the first star. Okay, and next take out the metal disc and observe the angle of refraction. Do the same for various angles. Find the corresponding angles of refraction and note them in the table drawn. So here we are performing this experiment from 10 degrees, 20 degrees, 30 degrees, 40 degrees, and we measure the angle of refraction. This angle of incidence and angle of refraction value we should note down in the table. Okay, like previous activity. In previous activity, the drawn one table, no, we measure the angle of incidence and angle of refraction value, no, like that here also we should do, and use the data in the table too, and find the refractive index of a water. So do not take up this activity for angle of incidence greater than 48 degrees. Okay, so don't perform this activity more than 48 degrees. Okay, you will learn the reason for this in the following sections. So you will observe that in the above activity, R is greater than I in all cases. That means when light travel from water to air, means denser to rarer media, then what happened? Angle of refraction will be more than the angle of incidence. So from the above angle of incidence and the angle of refraction value, we can find out angle R is greater than I in all cases. That means when light travel from denser to rarer, means from water to air, then what happened? Refracted ray move away from the normal, and angle of refraction will be more than the angle of incidence. So from this activity we can generalize that when the light ray travels from denser to rarer, it bends away from the normal and R is greater than I. So already we discussed in previous topic also. What is that? Light travel from denser to rarer media. Okay, V1 and V2. That time V2 is greater than V1. Okay, in that also we discussed. So till now we discussed what happened when light travel from denser medium to rarer medium. So here when light travel from denser medium to rarer medium, R is greater than I, means angle of refraction is more than the angle of incidence. So you will observe that in the activity R is greater than I in all cases. That means when light travel from denser to rarer media, means water to air. So it behaves in an opposite way to the way to that we observed in lab activity 1. From this activity, we can generalize that when light ray travel from denser to rarer media, it bends away from the normal and R is greater than I. Is there any relationship between the angle of incidence and the angle of refraction? Is there any relationship between the angle of incidence and the angle of refraction? So the relationship between angle of incidence and the angle of refraction can be given by n1 sin I equal to n2 sin R. n1 sin I equal to n2 sin R. This is called as Snell's law. Snell's law, sin I by sin R equal to n2 by n1. We know that n2 by n1 equal to v1 by v2. So sin I by sin R equal to v1 by v2 we can write. So when light travel from one medium to another medium, the ratio of speed is v1 by v2 and the ratio of refractive indexes is n2 by n1. Hence the angle of incidence uh, hence the angle of reflection and the angle of incidence will be follow sin A by sin R equal to v1 by v2. So when light travel from one medium to another medium, the ratio of speed is v1 by v2 and the ratio of refractive indexes is n2 by n1. Hence the angle of reflection and the angle of refraction will be follow sin A by sin R equal to v1 by v2. So Snell's law what? Sin A by sin R equal to n2 by n1 means it is the ratio of sine of angle of incidence to sine of angle of. Now we will discuss derivation of Snell's law. Consider the following analogy to derive it. Let us imagine that person has fallen out of a boat and is screaming for help in the water at a point B as shown in the figure. So here once you observe the picture, a person is fallen in the water. Okay, so the person is at the point B and is seeking for help. Okay, so here we are at A. In this picture we can observe A and points B. No, we can observe point A, X and B. So B is nothing but the person fall in the water, is seeking for help, and A is nothing but we, means we want to save that person. Okay, we are at point A. What is X? X is the shoreline. The line marked through the point X is the shoreline. So let us assume that we are at a point A on the shore and we saw the accident. So now we are at point A and we saw the accident. In order to save the person, we need to travel a certain distance on the land and certain distance in water. So here the person fall in the water. No, we want to save the person B. So now we are at A. To save the person B, so we have to travel on the land and we have to travel certain distance in the water also. So we know that we can run faster on the land than we can swim in water. So we can run very fast on the land, but we can move slowly in the water. So what do we do to save the person? To save the person, what we will do? Which paths enable us to save the person in the shortest possible time? Do we go in a straight line? So to save the person, we will select the path which is taking least time to travel. Yes or no? Yes. Okay. So here by careful thought, we would realize that it would be advantageous to travel at a greater distance on the land in order to decrease the distance in water, because we go much slower in water. So here the person fall in the water. So we are at A. To save the person, we have to select the path which is taking least time to travel. So here we can move fastly on the land. So we can move slowly in the water. So that's why we have to choose the path which is taking least time to travel. So by careful thought, we would realize that it would be advantageous to travel a greater distance on the land in order to decrease the distance in water, because we go much slower in water. For whatever speeds on the land and water, the final path that one has to follow to reach the person is ACB. So to reach the person, we have to follow the path ACB, and that this path takes the shortest time of all the possible paths. If we take any other route, it will be longer. So to save the persons, we have so many paths, means to reach from A to B, we have so many paths. So we can observe that paths in figure. So we have so many paths to save the person that we can observe in this figure, like ADB, ACB, like that we have so many paths. Okay, but we have to select the path ACB, that path taking shortest time when we compare with the all possible paths. Okay, if we take any other route, it will be longer. Okay, so if we plot a graph for the time taken to reach the person B against the position of at any point when we cross the shoreline, we would get a curve something like as shown in the figure. So here we have so many paths no to reach the person B. So if we plot the graph by taking the time on x-axis, by taking the distance values on y-axis, and we will get the graph which is shown in the figure 6 to be like that we will get. Okay, so in this graph the distances from the point y to the points like DC are taken as the value subset. Okay, so if you plot the graph between time and distance, then we will get the graph as shown in the figure 6 to be. Here where C is the point on the shoreline, here C is the point on the shoreline corresponds to the shortest of all possible time. So this C is the point on the shoreline. This path is taking shortest time to reach the person B. So let us consider a point D on the shoreline which is very close to the sea, such that there is essentially no change in the time between the path ACB and ADB. So here we can observe the paths ACB and ADB like that. Okay, so here ACB path is there. Okay, that is taking least time to save the person. So near to C one more point D is there. If we choose the path ADB, that also taking least time to travel, least time to save the person. Okay, so in this, which is better, ADB is better or ACB path is better? Now we will discuss. So here to save the person we have to select the path ACB. Okay, so but near to C one more path ADB also there. So these two are approximately taking same time to save the person. Okay, so in this, which path is better to save the person, ACB or ADB? Okay, now we compare that the paths ACB and ADB. Okay, so once you observe the paths AD and AC. Okay, so here one horizontal line is there, no, that is shoreline, means above the shoreline land is there, below the shoreline water is there. Okay, once you observe the paths AD and AC. Okay, so here we are observing the paths AC and AD, no. So these two paths on the land. If we draw a perpendicular line on this, okay, if we draw a perpendicular line DE, so draw one perpendicular line DE on the point D. Observe the paths. So here if we are going through the ACB path, E to C distance we have to travel on the land more. Okay, so when we draw a perpendicular line DE at point D, okay, so E to C distance we have to travel more on the land. Okay, at the same time observe the paths CB and DB. Okay, observe the paths CB and DB. Now draw one perpendicular line at point C. Okay, draw one perpendicular line CF at point C. Okay, so when we compare these two paths CB and CD, so we have to travel the DF distance more in the water. Okay, we have to travel D to F distance. Okay, D to F distance more in the water. Okay, when we compare with the path CB. Okay, C to B distance observe and D to B distance observe. When we compare these two paths, so D to F distance, that much distance more we have to travel in the land, but we will go slowly in the water, no, so it is better to travel on the land more. Okay, when we compare the paths ACB and ADB, we have to we can travel more distance on the land, by that we can save the time to travel in the water. Okay, so first to look at the paths on the land as shown in the figure 6 to see. If we draw a perpendicular DE, between the 2 points D, we see that the path AD on the land is shortened by the amount of EC. On the other hand, in water, by drawing a corresponding perpendicular CF, we find that we have to go the extra distance D to F in water. In other words, we gain a time that is equal to go through the distance EC on the land, but we lose the time that equal to go extra distance DF in water. So, if we select the path ADB, so D to F distance we have to travel extra distance in water. Okay, so but we can travel in water slowly, no, so that's why it is not better to go through this path. Okay, next, these times must be equal since we assumed there is no change in the time between two paths. So let the time taken to travel from E to C and D to F is delta t, and V1 and V2 are the speeds of running and swimming. So from the figure 6 to C we get, so speed on the land is V1, speed in the water is V2. So here the time taken to travel from E to C and D to F is delta t. So from that we can write like this: EC equal to V1 into delta t. Okay, EC equal to V1 into delta t. We know the formula of speed, V is equals to S by T. V equal to S by T. Then S is equals to what we can write? V into T we can write now. Like that, here EC is nothing but distance. So distance is equal to speed into time. EC is equals to V1 into T we can write. At the same time, DF is equals to what we can write? DF equal to V2 into T. So here the DF is equals to V2 into T. So here EC is equals to V1 into delta T. We can write like this: delta T is equals to EC by V1. Okay. So delta T is equals to DF by V2. So from these two we can write like this: EC by DF is equals to V1 by V2. So this is equation number 1. Let I and R be the angles measured between the paths ACB, and normal NN is perpendicular to shoreline X. So here I and R are nothing but angle of incidence and angle of refractions. Okay, that is measured between the paths ACB, and NN is a normal. So from this figure 6th C we can get sin I equal to EC by DF. Sin I is equals to EC by DF. So we know that sine of any acute angle in a right angle triangle can be defined as the ratio of opposite side of that angle to hypotenuse. So here we have two right angle triangles now. Okay, so what are that? DEC and DCF. Here we have two right angle triangle. What are that means? DEC and DCF. Okay, so when we draw one perpendicular to incident ray. Okay, incident ray is AC. Draw one perpendicular to AC, that is DE. Then one right angle triangle it will form DEC. Okay, so now draw one perpendicular to refracted ray DB. So which perpendicular we drawn? CF. So CF, that perpendicular line we drawn to refracted ray DB. Okay, so one more right angle triangle is formed, that is DCF. So here we have two right angle triangle, DEC and DCF. So we know that sine of any acute angle in a right angle triangle can be defined as the ratio of opposite side of that angle to the hypotenuse. Okay, so from this we have two right angle triangles now. So what are that? DEC and DCF. From that, sin I equal to EC by DC. Then EC equal to, we can write DC sin I. Next, sin R equal to DF by DC. From this we can write DF equal to DC sin R. So substitute this EC and DF values in equation number 1. What is that equation number 1? EC by DF equal to V1 by V2. So EC is equals to what is there? DC sin I, and EF is equal, next DF is equals to what is there? DC sin R. Substitute that value in the place of EC by DF. Okay. So equation number 1 is EC by DF is equals to V1 by V2. EC is equals to DC sin I and DF is equals to DC sin R. Now substitute these values in equation number 1. Then what will come? DC sin I by DC sin R equal to V1 by V2. V1 by V2 is equals to, we know, N2 by N1. So DC get cancelled. Then what will come? Sin I by sin R equal to N2 by N1. Otherwise that we can write sin N1 sin I is equals to N2 sin R.